So we stopped by explaining what is a cellular transformaton and that it's pretty clear that we can characterize it by the same Curtis-Hedlund-Linden theorem we used for cellular automata. Another very simple generalization is what does it mean to be a cellular transformaton of some packed configuration spaces? So we can call it the packed version of the Curtis-Hedlund-Linden theorem. So let phi be a mapping from S to the Z to the D to some T to the Z to the D. So we always assume these are finite state sets. And let V and W be two tiling bases. So W be be two sequences of the linearly independent vectors in Z to the D. And also let's choose D, V, and EW, some two tilings. Two tilings of Z to the D. Then the following are equivalent. So first of all, phi is continuous. And commutes not with all shifts, but in all shifts whose vectors lie in the corresponding images of these two bases. So basically, and for all vectors from Z to the D, phi composed with the shift mv times v is the same as shift with respect to the other bases composed with phi. And the second condition is that the packed map, which we can denote like the source space being packed with this tiling and the target space being packed with this tiling. So this should be a map which first unpacks the packed space. So we use ODV inverse, then uses phi on just S to the Z to the D to get us here, and then we pack again on the target space by the different tile here. So this is a mapping from the packed space SD Z to the D to T TE, well, something is not, TE Z to the D. There is nothing to this. It's actually an exercise. So, I mean, if phi is continuous, obviously this is continuous because it is composed with continuous maps, and the other way around because they are bijective. And in some sense, if phi commutes with these sorts of shifts, then once you pack the corresponding spaces with respect to the tilings with the suitable bases, these shifts actually become any shifts on that packed space. So you just end up with a mapping which commutes with all shifts on the packed space. So yeah, so okay, I should finish what I want to actually say. Is a cellular transformaton. That's the key. Cellular transformaton. And this, in some sense, concludes our quest for understanding what could be a reasonable encoder and decoder, which is somehow compatible with the cellular automata. It's going to be exactly maps that, after suitable repackings, they can be viewed as cellular transformata. So those are definitely simple because they're just described by a finite description that is the local rule and the tilings. So we can conclude with a definition. A map phi from S to the Z to the D to T to the Z to the D, which satisfies one or two, which are equivalent from above, is called a computationally admissible map. Mm-hmm.
Here in the first point in the theorem, isn't there two V's that mean different things?
This is a capital V,
Oh, okay.
which refers to the basis. Okay. I just like vectors to be V, but you can put some different letter, which hopefully makes it clearer. Well, good that it's clarified. Are there any other questions? Mm-hmm.
What is a cellular transformata?
Transformaton.
Yeah, what is that?
We just defined it. It's like a cellular automaton, except for the source and target configuration spaces need not be the same. Yeah.
Yeah, I thought it was something else.
So good to clarify. So, yeah. So we say something about a map on the original spaces, but we use the language of the packed spaces. We want this map to be a cellular transformaton on the packed space. So hopefully we can finally proceed with defining what global simulation means. Let's do it. So let's fix two cellular automata in the same dimension. So B cellular automata. Okay, cellular automata. We say that B globally simulates A if, now you have a rather long laundry list of conditions. So if there exists some time delay tau, which is a positive integer, some shift vector v, so now we will have only one v, so I can call it v, hopefully. Yeah. And a partial surjective map D, which leads from the configuration space of B onto the configuration space of A, such that for all configurations from the domain of D, which is some subset of D to the Z to the D, it holds that if we look at this geometrically transformed global rule of B, and we look at what it does applied on C, and we decode that, it's the same thing as first decoding and then applying F. That's not all. And where D is computationally reasonable in the following sense. So there exists some tiling dv of z to the d such that D is doing essentially the same thing as some cellular transformaton on a packed space, where D tilde is now a mapping from this packed space. So it's a partial map to S to the Z to the D, is a partial cellular transformaton whose domain dom D tilde, which is a subset of these packed configurations, is another computationally reasonable object, so a subshift of finite type. So this tells us something about the fact that we can implement D as a computationally admissible map, but we want the target space not to be a packed space. We just want the source space to be a packed space. This will be important when we want to show that global simulation is transitive. It makes it much more friendly to work with that. And second condition on the decoder is we would like it to have a computationally reasonable inverse, such that if we start with a configuration from A, we have some way to map it into some configuration of B in a way that corresponds with this decoder in a computationally reasonable way. So there exists a right inverse E from S to the Z to the D to T to the Z to the D of D. So this just means that if we first encode and then decode, we get an identity on the configuration space S to the Z to the D, and E is a computationally admissible map. We will take our time to unpack this. So we can call this star now. So just to finish the definition, in such a case, we write that A is, let's say, a curly smaller or equal to B, because in some sense B does have richer or equal dynamics to A, and say D is the corresponding or let's say is the decoder and E is the encoder that witnessed this. That witness this. So first proposition that we don't have time to prove, but there is nothing interesting in the proof, it's just a straightforward verification, is that E is reflexive and transitive. Which is something reasonable we could want from this relationship. So every CA can globally simulate itself where the encoder-decoder are identities, the shift vector is 0, and the time delay is 1. And you can also show that if B simulates A and C simulates B, then C globally simulates A by just composing the encoders and decoders and verifying that everything works. The second proposition that we will verify so suppose that B globally simulates A with the notation from the definition. Then, for all possible iterations, we also get that when we decode, after iterating this transformed global map n steps, it corresponds to decoding and simulating or iterating n steps the global rule f. So, and for all C in the domain of D. And in particular, we can apply the map E from the right to this. And then we simply just obtain that D after we decode n iterations of this transformed map of an encoded configuration E C prime is the same as for every C prime in S to the Z to the D. So this may look much more familiar because this is indeed the diagram we saw at the beginning when we talked about the intuitive thing we would like from global simulation. It means no matter what configuration we start for A, we can encode it into some configuration of B, iterate B some number of time steps, and then decode, and we obtain exactly the same thing as iterating F. So going from here to here is just applying E from the right, so that's pretty simple. And I could explicitly write, so you can prove this by induction on N, or you can draw a commuting diagram. I recommend drawing commuting diagrams. So if we start with the domain of D, then this gets decoded into or onto S to the Z to the D. Here we apply F. Here we apply sigma V composed with G tau. And here we again apply the decoder. So essentially the observation is that this commuting diagram is equivalent to the condition. I just drew, it's just a single star, excuse me. So one thing we can notice is if we start with a configuration which is in the domain of the decoder and we apply sigma V composed with G to the power of tau, we have to end up with something that is still in the domain of the decoder because we are decoding it here. So truly the map sigma V composed with G to the tau restricted to the domain is a self-map between of this space. And then it just says that you can first apply this map and decode, or you can first decode and then apply F and this diagram commutes. And now if you want to show that it holds for arbitrary iterations, you just, I should have left more space here. You can just draw another diagram here. So this is the exact same diagram, so it also commutes. And if you have these two commuting diagrams, you also commute in this way, which exactly gives you the second iteration. And you can draw n of them if you want to convince yourself that it's for n iterations. So is there something important I'm forgetting to tell you? Yeah, I think we can move on to just trying to understand this even more. What I find quite helpful is, let's say, the algebraic viewpoint on this. On the definition. So, if we start with the condition from the definition, on the domain of D, and if we notice that D is just can be decomposed into a packing and a cellular transformaton, then we can substitute this in this condition. So we just get this condition. And here we can notice this is exactly the global map of the CA, which is just the geometrically transformed CAB by the packing dv shift v and time delay tau, which now operates on the packed space and has, yeah, we can call this G tilde. So the packing, we initially hid it in the decoder, but you can explicit it and instead view this as a transformation of the cellular automaton. And now here comes the algebraic part of this. So proposition. So in this case, we can, let's say, simplify this commuting diagram. So this condition is equivalent so now this is on the domain of the cellular transformaton d tilde, clearly. So is equivalent to the following diagram. We can start with the domain of d tilde. We can apply this g tilde restricted to this subspace, and we have to end up in the domain of d tilde again, because again we have to then be able to decode. Or we can first decode and then apply f. So what this means is that if we look at the dynamical system whose space is exactly the domain of the decoder, and the global map is just this transformed G restricted to this domain, this is just a subsystem of this transformed cellular automaton. So simply because this is really like a subset of this packed configuration space, and we just showed that if we restrict the global map to this subspace, it is invariant under it, or let's say it goes back in that subspace. So that's just a trivial observation. Yes?
What is 2 stars equivalent to?
To this commuting diagram. So, yeah, it should be pretty obvious that this is really a subsystem of our transformed, geometrically transformed B. And second, if we now look at the condition in this form, simply means that our cellular automaton A is a factor of this intermediate system. And moreover, both this subsystem and this factor are, let's say, computationally reasonable, in the sense that this subsystem is a subshift of finite type. So we just have a finite description for that. And this factor what is the vector map? It's just d tilde. So with d tilde, the vector map, which is a cellular transformaton. So it is again an object with a finite description. So to summarize this, we could say that A is simulated globally by some CAB if and only if A is a computationally reasonable factor of a computationally reasonable subsystem and now of what? Not of B, but of this geometrically transformed B, where we allowed for some packing, some time delay, and some shift. And what the computationally reasonable means? So this means the factor is a cellular transformaton and here what computationally reasonable means, it is induced by a subshift of finite type. So now you have a lot of perspectives how you can look at global simulation. But hopefully it's quite intuitive. We somehow want the dynamics of B to contain the dynamics of A, modulo some details. And what are the details is we allow to massage the space of B by some repacking, some shift, and some time delays. And then the way we can find A inside B is through a computationally reasonable factor of a computationally reasonable subsystem of that space B. Maybe it's a nice time to show you a cool example. So back to, let's say, examples that might elucidate something. So first of all is that, let me double check. So first of all, you will have a chance at the exercises to verify that if you remember elementary cellular automata and some basic equivalences we introduced between them, which was based on exchanging the role of the state 0 and 1 or exchanging the role of the left and right neighbor, it is quite easy to show that for all such cases, it is also the case that if these two elementary CAs are in such a relationship, then one can globally simulate the other one. What I want to show you is that global simulation gives a much richer relationships between cellular automata, which would not be uncovered just by these simple geometrical transforms we studied earlier. And hopefully this example is simple enough that it can elucidate it. So let's consider two rules, Rule 4 and Rule 76. They're both very simple. They do nothing new after the first iteration. Rule 4 specifically, everything dies out except for a single black cell surrounded by zeros, which preserves. Rule 76, not everything dies out, but whenever you have a black cell only surrounded by black cells, it dies out. Dynamics is pretty clear. So let's now define two local maps. Spoiler alert, this will be somehow the local maps of the cellular transformata that implement the encoder and decoder. So the local map, which will encode, takes a single 0 and multiplies it to 2 0, takes a single 1, multiplies it to 2 1. The decoder decodes 1 1 to 1, everything else to 0. And this already induces the following relationship. If we start with any potential configuration of the elementary CA4, we can encode it using this epsilon, where we just cell by cell map each cell into this supercell of size 2. And then if we start iterating the local rule, or if we start iterating the rule 76 on this space, well, for instance, for 2 iterations, but it really does not matter, and then we decode, we actually exactly get the dynamics of the elementary CA4. So the intuition is that both rule 4 and rule 76 are able to tell something about edges of blocks that are just black. And if you encode these edges smartly into the CAs, then they will end up doing the same thing. So what we can do to make this much more visible is, again, squint our eyes on this diagram of 76. We can forget each of these intermediate iterations, and we can color based on what basically black, or this dark color gets decoded to black, and all the light colors that get decoded to white. And it still takes a bit of work. Specifically, you have to define the domain of the decoder to really show that Rule 76 globally simulates Rule 4, but it is not very difficult. That's an exercise for you. So hopefully that should convince you that Rule 76 does simulate Rule 4, if we kind of represent the information well enough for Rule 76 to do that. Any questions? Good. So what's fun is that it works the other way around too. So Rule 4, which maybe looks a bit more simple, can also globally simulate Rule 76. So now we have to use supercells of size 3, and you don't need to go into too much detail. But again, if you use a suitable encoding, and then you let the elementary CA4 iterate, it's going to do exactly the same thing as elementary CA76. So this somehow means that these two automata are equivalent modulo the relationship of global simulation. It does not necessarily mean they share the exact same dynamical properties, but from a computational perspective, whenever one of them can simulate something, the other can simulate it too. So it's kind of, let's say, a richer way or a richer lens through which we can look at the space of cellular automata. And a very fun future pursuit could be to really try to push the number of unique CAs up to this relationship to show whether there really is something like Wolfram classes where you just end up with some canonical examples from some computational representatives of a particular CA class. Yes?
Do we know anything on that aspect?
No, so this example I found like 3 years ago. So it's not even that well known, for instance. Yeah, but that would be very cool. Well, the problem is just to find these relationships for more complicated cellular automata. So one last definition to give you today is a very important one, is that of global universality. So we say that B can globally is globally universal. Oh. So obviously this is a cellular automaton. If it can globally simulate any other d-dimensional CA. We have seen one example of this, which was Game of Life, which was a truly astonishing result, specifically because Game of Life is a very compact CA with just 2 states. Yet somehow, if you zoom in from a very smart encodings, you zoom out, you can uncover that Game of Life hides the structures of many other cellular automata. But it does not have, global universality is not something magical. So I'll show you an example of a one-dimensional globally universal CA that I constructed 2 summers ago when I was curious how it could work. And let's say the way so there are no other known one-dimensional globally universal CAs, but this one is puristic in the sense that the encoders and decoders used are in some sense minimal. I don't want to go into too much depth about this, but yeah. So what I did is I had one fun week when I wrote down this rule table of, let's say, 63 states. It was a long week, but it was quite fun actually. Let me hide this. So the point is, for Game of Life, why it is difficult is that it is a given CA, and now you have to uncover all its structures, but here I had the liberty to really define it however I want. So here it's just defining the encoders and decoders. And here is an example of a CA that we would like this particular one. The local rule is fixed, I showed it to you, that we wanted to simulate. So for instance, this is rule 110. You could define other rule tables. This is what, let's pick some funner, I don't know, whatever. Let's pick this one, for instance. So this is a particular diagram of rule 110 that we would like our universal CA to simulate. So now I'll show you the first 10,000 steps of the simulation. Obviously, it's very inefficient. But just so you can have a sense of how this could even potentially work. So what you see here is a $sign, which is a delimiter of one huge supercell, which ends. Oh no, we don't see this from the beginning. We have to start with a fewer number of iterations. Great, this is better. So here is the start of a supercell. Where does it end? Here. So these approximately 100 states of this universal CA represent just one state of rule 110. And what kind of information does it hide? Well, these 3 tildes essentially tell you if there are 3 of them, this cell represents a 1. If there were just 2 of them, it would represent a 0. So here we're representing this cell, so it's a 1. And then this huge rest is encoding the local update rule of rule 110 in a specific way. This is, let's say, again, 2 underscores represent 0 and 3 underscores represent 1. This is, let's say, saying what is the middle state, what is the right state, and what is the left state, and then what is the outcome. So for instance, if the middle state is 0, right state is 0, left state is 0, the outcome is 0. If the middle state is 0, the right neighbor is 1, and the left neighbor is 0, then the outcome is 1, and so on and so forth. And now each supercell has one active signal, which first kind of wakes up this supercell and tells it, okay, we will now be interested in what is the central cell. And whenever the central cell matches this expression, we will mark it by saying, we have a first match. And this is indeed what happens when this signal bounces back. It kind of activates this first cell and says, we are looking for what is the first state, what is the central cell of this huge supercell, because this part has no information about where this state is stored. So once this information travels all the way back, it again bounces off. And now it's time to actually propagate the information, which is now encoded in these 3 whatever signals, which means this is a state 1. And this signal first just bounces back, and now the matching starts happening. So it's going to multiply for each of these little rule table inputs. And whenever, so for instance here the middle cell is 1. So it matches the actual middle cell of this, or the middle state of, it matches the state of this cell. So this question mark becomes like, this is a hit. This really aligns. Here it's also a hit, but as we, so for instance here, the central cell was encoding the input 0, so here it's a miss. And now you can see this starts iterating, but now we kind of move it, like bring in the information from the right neighbor, and lastly we bring in the information from the left neighbor, until exactly one of these will have 3 hits, and all of them will have at least 1 miss. All of those that have at least 1 miss will kind of forget that they ever were questioned about the outcome of this rule table. And just the single one which has 3 hits will realize, okay, I'm the right part of the rule 1/10 rule table, which now governs what is the next state of this supercell and propagates that information back to where that information is stored, which is this tilde expression. So it's really just engineering your own signal transmissions in a one-dimensional world, but hopefully it's not completely magical. So it should not be surprising that in every dimension you have a globally universal cellular automaton. What we will discuss next week is that there are Turing-complete CAs which cannot be globally universal. One very interesting example comes from reversible computation, and it has a pretty interesting historical discussion. But I think for today, this can be it.